see this. This will not be on the exam on Friday. Friday goes up to 4.2. This will be on your last exam, coming up later on. It says solve this log base 5. Now, I don't think I've done this problem yet. X plus 6 plus log base 5, thank goodness they have the same base, x plus 2 is equal to 1. And they want us to solve it. Now, of course, I love to get responses from my students. Guys, does anyone have an idea of what on earth, if you're facing this on the exam, what are you going to do? Yes?
You could make it log base 5 x plus 6 times x plus 2.
And why?
It was product property.
Thank you. Exactly what I'm talking about. So you rewrite that, put it back together with the help of the product. Now, that's step 1. That's the product property. Now, step 2, don't lose it now. Now what? Thank you. Change that was just given to me into an exponential. In other words, tell me what it means. What it means, base 5 raised to 1 is equal to this. Is that true? Now the word log's gone. You told me what it means. And now after you told me what it means, this means 5 is equal to, let me expand this out. This is x squared, that's like 8x plus 12. We're into a quadratic. Better yet, x squared plus 8x, what is it guys, plus 7? I'm doing it quickly. And I'm hoping factors, if not, I'll use quadratic formula. And I think we lucked out here on this one. I think it factors, guys, what is it? X plus 7, x plus 1. Is that true? Right? Split this up. I'm looking at, for solutions, to consider these. Now, you're doing the test or the quiz. You have one like this. You say, Professor, I've got the zeros, I've got the answers. And all of a sudden you might get your paper back after I score it. You'll say, ooh, I missed something. You took a point off. What might be the reason that I may take a point off? It may not happen here yet, we haven't done it yet. But what should you be cautious about? Yeah, do both of those check. And I'm not asking unless you want to do a full check. But there's something there that should tell me which one of those not checked. If so, disregard it. Guys, I'm going to look back at this myself, and I'm not going to try a full check if I can avoid it. Let's check this. The first term given to me was log of x plus 6, base 5, of course. And the restriction on log, the domain, that x plus 6, we discussed domain for a log, must be that. That means x must be greater than what? Negative 6. There's a restriction on this one. X plus 2 for that log for domain must be that, and x must be greater than negative 2. Is that true? Now, if either one of these, or both, do not fit those restrictions, I can't use them. They're not in the domain. Now I got negative 7. Is negative 7 greater than negative 6? No. Is negative 7 greater than negative 2? No. Is it? Is negative 7 greater than negative 2? So I don't think negative 7 placed here would even fit the domain. Negative 1 may not work. Who knows? Is negative 1 greater than negative 6? Yeah, compare those two numbers. It is. Is negative 1 also greater than a negative 2? Looks like then, there's the answer. And to disregard 1. Now you guys just want to do a full check. Let me show you a full check on that negative 7. That negative 7 looks like it's not going to work. If you did a full check, you're doing this. Log base 5. You're replacing x with a negative 7, which makes that negative 1 inside. We'll do it quickly here, guys. Plus, oh, right there's the issue. I don't do anything else with it. After I replace x by -7, a -7 plus 6 gives me what? -1? And you can never have a negative inside here for a log. We discussed that in class. That would be another way to see that -7 can't be used, Professor. -5, let me go, not -5, -1, let me do it. If I replace by -1, we're saying it looks like it meets the constraints here. Let's put -1 in though. -1 plus 6 is 5, so this becomes log base 5 of 5. If I put in -1 here, -1 plus 2 gives me a 1. So this is log base 5 of 1. You step it back and look at it. -1 plus 6, got it. -1 plus 2, got it. Guys, what is a log of 5 base 5? 1. What's the log of 1 base 5? 0. 5 raised to the 0. Does that give me what we want? Does it check? Does that give me, through that reasoning, a check there? So all I'm saying is be cautious, check, if you have one of these to work. Also, I know on the handout I had that for sure. Another one here coming up, beautiful, hang on, I'll find it. Yes, the next one. A log, part B. I don't want to leave this here shortly. I'm not going to work all these guys. Next one looks like it's log base 4. And it looks like it's x squared subtract 9. It says subtract log base 4. It looks like it's x plus 3 is equal to 3. Can someone tell me what might, with the help of logs from yesterday, what might I want to do here? Looks like quotient. It's asked me to do quotient property. So rewrite this, guys, as one log, a single log. Markers will work. Single log of a quotient of x squared subtract 9 over x plus 3. Right like that. And that's equal to, looks like 3 from your handout, if I copied this down correctly. And it's log base 4. Is that true? Okay. Now, partial credit. You don't have solved it, now what? That's quotient property. Now what? I could change that log form into what, an exponential, or describe what it means. I could do that. But if you do that at this point, can someone tell me what on earth does this mean? In other words, you're going to drop the word log. Tell me what it means in an exponential form. What does it mean?
4 to the power of 3.
There you go, that's what I want to hear.
Minus 9 over x plus 3.
That's what I want to hear. Thank you. Thank you. That's a critical step there. Now the word log's gone. Show me what it means. Therefore, I should be able to finish this up. Now, guys, I noticed, and I think a student will tell me here, I think in this case, the numerator factors, before I jump into it further, over this, which really is a big help, because I think these two cancel. Is that true? And therefore, I'm going to end up with only, what, 64? 4 cubed is 64 is equal to x subtract 3. Oh, look at that. To solve for x, x is 67. Does that 67 make sense, the way we approach this? Woo! Now, if you want to go back and check it, do a full check, I see it would be awkward, as you know what, to put a 67 in here, but you got to square it. Then subtract 9, do your business. And down here also 67 plus 3, and do your business there and see if it eventually works out. But I think it's 67 the way it looks, guys, the way we did this. Are we okay with this? On this one? Yes, no? Now, I brought this one in. It may not be on your handout. Oh, no, hang on. There's one more on the handout. Letter C. It's on your handout. I'm looking at actually number 6. All of a sudden you see this, no logs. 3 raised to the x is equal to 14. Now before I do it, guarantee you, if on an exam or a quiz, this had been 27, every student in class would get the answer. The 3 raised to what power would give me a 27? If that had been 27, and it is what? 3 cubed. It wasn't 27. I think again, letter G, or number 6 there, was 14. So guys, how am I going to deal with it? We're going to get an answer.
Just
Rewrite it. Put it in log form. So now it's in so-called exponential form. Now put it in log form. We'll rewrite this as this means log.
base 3.
Absolutely. Base 3, come to work. 14 is equal to, there's your answer. Strange answer. Log of 14 base 3. And since we're not allowed to use calculators, we just leave it like that. At least we solved it. Now the last thing. Gee. Feel much better about this closing down chapter 4 before I get back into chapter 5. I brought this in. Let me check and see if I did. Yeah, I did. And this is much like one you see on your handout, but I chose this. E to the x plus e to the negative x is equal to 6. I will solve that for x. I'll ask one, take a close look at it. I need some help here. Any ideas? This one's tough.
Natural log on both sides.
What do you?
What was natural log on both sides?
Now, if I put a natural log on each side, I would be doing this. Hang on, wait. If he said, Professor, introduce a natural log on each side. Now, if I do, it looks like this. And there's nothing wrong with that, doing that. But is it going to lead me to where I want to go? What do you have in mind after that? I don't think it's going to take me anywhere.
Maybe get the power of x out of the 1 by
I think at this point right here, what Wayne just told me to do, I don't think it's going to take me to where I want to go. I know what you'd love to do. You'd like to say, oh, Professor, is there a property here I could use here? No, this is a sum, not a product. So how do we have a property to use here? Wayne, there's nothing wrong with doing that, but it's not going to take me to where I want to go. This one's a little bit tougher. That's why I saved it for last. Any other ideas?
So when you divide them,
Oh, do it again.
when you divide them,
Divide them into more what? How?
EX divided by E minus X.
Ooh, you're getting close.
Oh,
You're getting very close to what we're going to do here.
change to 1 by e power x.
Well, you're concerned about this.
Yeah, you can move 1 by e power x.
And she says I can rewrite that, if it'll help. And PK as what? What does that look like rewritten from algebra? And before you give me the answer, what would this look like? What is that?
1 by 2.
1 over
1 by 4.
1 over 2 squared, which is 4. And that really says 1/4, doesn't it? Now do the same thing here. What does that look like? 1 over e to the x. That has changed. Of course, I still have this. Got this. It's equal, I threw a 6 in. Guys, that e to the negative x was the key there. I'm not quite finished with the problem, though, but I had to change it from 1 over e to the x, is what it means.
Same denominator.
There you go. Now combine these two with a common denominator, and I gotta be careful, you gotta be careful on this last problem. Can anyone tell me? I notice that under or over 1 right now. What am I going to use for a common denominator on the left-hand side to begin with?
EX.
E to the x. I want to put these two together with e to the x. Well, if you want e to the x, this one's missing. Like I put it in. Top and bottom, numerator, denominator. Now the question is, now they're at least over the same denominator, e to the x. Anyone, be very careful. Anyone tell me what this now in the numerator top here, e to the x times that additional e to the x?
X squared.
See, you would think it was e to the x squared, and it's not.
Equal
I get that answer all the time. What was
to,
it?
equal to x.
Now, she's telling me it's e raised to the 2x for this, still got plus 1 over here on this side. Equal to 6. Now, let's go back. Okay, why would you say 2x? Give me a class reason. Because I, as a student, I would probably say x squared. Why would you say add them, Professor? X plus x, don't multiply them. Why?
Six multiply.
Yeah, because down here is multiplication, isn't it? If you multiply, look at this. Please tell me, it looks much like this from algebra. You add the exponents. That's what it looks like. E to the x times e to the x, e to the x plus x, m plus n, e to the 2x. Wow, what a problem. Am I finished? Wayne, I'm not finished yet. Give me an idea of what else might I do here. This is looking crazy.
I think it's, 4, not 6.
Where's the 4? Where?
Equal to 4.
No, that was on the handout. I'll change mine.
Oh,
I changed to a 6 for a reason. Now what?
Now you took the long and used the proper.
Okay.
multiply equal x to the other side.
You mean multiply these two together? And rewrite this as e to the 2x, hang on. I guess a plus 1 is equal to 6 e to the x. She wants me to do that. There's nothing wrong with that. Multiply both sides by e to the x. Looking somewhat better. This is a crazy one. This is a crazy one. The one on the handouts, I think PK says what is it, a 4? And I put a 1 in there to make it a little bit more interesting. We'll see if it makes sense. Guys, now, we'll do this. Let's rewrite this as e to the 2x. This is tough. I'm going to move this over the 6 plus 1 and make it 0. Oh boy. Let me look back at all my work and see if you guys follow what I've done so far. Is everything correct so far? Now, can anyone tell me you're supposed to solve this? If it's a quadratic, I'll use quadratic formula. Or if I can factor, I'll factor.
Maybe we'll let you be.
Give me again.
We'll let you be e.
Yep, there you go. We're gonna let u be something. And let u be what?
ex.
Beautiful. E raised to the x. And what he's giving me here, that first term, e to the 2x, if you wish, could be thought of looking like that. That's still e to the 2x. It's rewritten. And he said, replace that e to the x with u. Guys, this becomes u squared, subtract 6u plus 1 is equal to 0. Now, what would you attempt to do? Either factor or, since it's quadratic, or use what? Quadratic formula. Now, guys, I brought this in because this one's crazier than the one you have on your handout. I think if you go through on the one on the handout with the e in it, yours will be more doable. Because I think if you try factoring, this does not factor. If I try quadratic formula, look at this. U would be equal to, by formula, 6 plus minus square root 36. Looks like we'll be a minus 4 on the end when you use quadratic formula, all over 2. Let's place my numbers into quadratic formula. Or this is u is equal to 6 plus minus, if there's no mistake, it's 32 of all things. Yes or no? 32 is not perfect. For a square root, can anyone break it down or simplify it for me?
2 square root 8.
Okay, even further.
4
Okay, I heard 4 square root 2. I think she's thinking about 16 times 2. Break it down further. Still over 2. Now at this point you could reduce this down, divide everything by 2, and have 3 plus minus, what is that, 2 radical 2? That's u. That's why I brought mine in today to show you rather than do the one on the handout. You guys should try the one on the handout. I think yours is a little bit easier than the one I just brought in. Yes?
I have a question, could you also complete the square with that, would that even make sense?
Hang on. You mean back here?
Yeah,
Absolutely you could, and it may save time.
yeah.
I've had students, when I score your quizzes or exams, I see some students they love that completion of the square. And sometimes it makes it shorter, and you get to where you wanna go, rather than use quadratic formula. You get the same result, you will, absolutely. Guys, got these? I'm not finished because u was representing what? E to the x. Look at this. So this says e to the x is equal to, at this point, I'm gonna separate them. I know I'm not running out of board space here. E to the x is equal to 3 minus 2 radical 2. Now there they are separated. Now, can someone tell me, the next part at least is easy, even on this complicated problem. Can anyone tell me what on earth, if this is possible, what on earth is the answer here for x? There you go, hang on. X equals, tell me, ln plus 2 radical 2. She's telling me, Professor, what you have here blocked off and the one you just gave me, PK, they're saying the same thing. These two are saying the same thing. Now if I try it on the other one, PK, help me out, x equals what here? Thank you. He says, Professor, these two are saying the same thing. They are. And I have x. They asked me to solve for x, and now I have x. What might bother you? Am I allowed to accept both answers? One answer, maybe neither should be accepted? What does that all depend upon? Someone tell me, what does that all depend upon? Because we're finished. We just have to decide, can we accept it? Can I accept this one? I'm not going to do a check on it. I can just, looks too strange. But can I accept it? And what would say, yes, Professor, go ahead and accept it? Yeah, for a log, any type of log, natural log, this part inside here has got to be what? Greater than 0. That's domain. This one is. This one bothers me. Right now it bothers me. Am I guaranteed that this one over here, 3 minus 2 radical 2, inside there is also, all that together, is that also greater than 0? If it is, I'll accept it also. Is it? If you sort of visualize 2 times radical 2, I think radical 2 is like 1.414. And you multiply it by 2, so you're going to get 2 point what, something. 3 subtract, you'll still get a positive response. Guys, both of those are acceptable. Who on earth would think? Where's the problem? Oh, here's the problem. Here's the original problem. Right now you have, I'm going to set strange answers. One is what? ln. We have what? 3 plus 2 radical 2. And with some thought, we're going to even accept the other one. Wow. We're doing pre-calculus. Now, am I going to do a full check on this? No. We're going to do a full check on this. Now, to make sense the way we approach this, so I'm hoping a student will try the one with the E on the handout and try it, and maybe have a question in class and say, Professor, would you work that one also? And I want you to have an opportunity to work it. There's one on the handout there for the E. Guys, I feel good about this. Any concerns here? Now, I wrote myself a note. I better watch my time here. Oh, I did. Here's the last thing I wanted to point out. This one, and I'm leaving chapter 4. Mr. Park, you know what? We may, you don't have the handout, I don't think. In terms of an extra credit problem, we may place that one that's on the handout I think there's one with an E in it. Let's try to find where it was. Wait, I got yours. It was e to the x, subtract e to the negative x equals 4. We may place that. You know what, let's do, of the 3, I think we'll just give them 3 problems. We can place that one for an extra credit. Okay, so you guys can try that. So you'll get that too. Thank you. Now, here's what I want to close down with. Here's what a student asked for on a problem you were working. A student gave me a suggestion, and I said yes. Let's just make sure all my students see it. I want to look at this. Directions, write this as a single log. Right, as a single log. In other words, this has been broken up for you. The properties have been used. Now they want you to put it back together and see what the original expression looked like. Guys, this one I think is interesting. I think I took this from a calc textbook. ln of x over x subtract 1 plus ln x plus 1 over x subtract ln x squared subtract 1. Step back and make sure everything looks good. Everything looks good. Woo! They've already used the properties for you. Now they're going to ask you, can you now be clever enough to put all that back together and tell me as a single log, just one log, not 3 logs, and put it back together for me. And there's some hints here. And those hints are, then I'll get some input from you guys. I'll see, this is a hint, this is a hint. As I put it back together. Now, can someone get me a start? Yes?
X over x minus 1 times x plus 1.
Okay, hang on just one second. So you said multiply these two together.
Yes.
Or make product. And exactly, because that plus sign there says if they've already separated and they got a plus sign, they've actually used product rule. And then what's this right here indicate?
Quotient divide then.
Quotient, divide. Quotient. That's being divided by, it's the quotient x squared subtract 1. At this point, that's what this looks like. It's a little messy, but that's what it looks like. Now you gotta clean it up. I've used the properties. To clean this up, guys, this one's not too bad. The x is canceled here. We bring it over here. I got ln at this point. I have inside there, I've got x plus 1 over x minus 1. All over this. I'm going to go ahead and factor this. The denominator is x subtract 1 times x plus 1. That's what we have inside blue. Looks like that now. Let's see if you guys agree. Clean this up further. I'll do it right here. This says x plus 1 over x minus 1 is being divided by this mess. That's what it says. And then to divide, you know how to divide here. You're going to do it as x plus 1 over x minus 1 times what? 1 over this. At this point. Yes or no? Woo! Canceling? Oh, I see x plus 1's cancel out. I'm left with, at this point, 1 over x minus 1 squared. Would you guys agree? So I did all I had to do, and it looks like this simplified into ln, at this point, 1 over x minus 1 squared. Oh, you want to write this x minus 1, x minus 1?
I mean minus square. So to take it out from denominator.
And make it what?
Just x minus 1.
I thought you had it. Now, I think, I sort of follow what you said here. We did all the work. By the way, guys, you agree at this point. Is this okay? All of a sudden, you're doing your work, you're a good, solid student, and you flip to the back of the textbook where the answers are, and you look at the answer they give, and it's not that. You start worrying, I thought I knew what I was doing. They didn't give that. So the answer, even though I say, as a professor, I would accept that. But it could be made to look a little bit better. And more than likely, if this were a textbook problem, they would probably have this answer in a different form. Does anyone see, just out of curiosity, what I could do here to rewrite this just a little differently?
X minus 1 minus square.
Okay, x minus 1 times x minus 1, I agree with that.
I mean, minus 2 instead of just.
Oh, hang on, oh, you want me to do this? I got you. I think. You want me to do that?
Yes.
Yes. This means this. And then guess what they do in the textbook sometimes? It used to make me so angry when I took a math course. I thought I knew what I was doing, I do all my work, and I'm so happy, and I flip back to the back to check the answer, and oh, that's not the answer. Actually, I had the answer, I just didn't simplify it to what they had. Could I simplify that further?
Minus 2 take 2.
They may move by power property, this out front, they may have the expression written as that. And that's what you see in the back of the textbook as an answer, where you had this, and then all of a sudden you become alarmed. And all they did as the author of the textbook, or those who work on that textbook, they just went a little further and had the answer like that. Okay? Thought I would point that out. Guys, chapter 4, unless I think of something later on, is, I think, done. I think it's done. I'm moving back into chapter 5, where we should be. Okay, I need to do a little erasing though. Please ask though, before I erase. Okay? Concerns here? Okay, I think we did a good job on that heavy chapter, chapter 4. Now, chapter 5, I think, based on what we've gone through with all this log business, you're going to appreciate chapter 5. I think. Did I discuss unit circle yesterday?
Yes.
I noticed this morning some of the professors around here are nosy. I noticed a couple of them looking in room 63 at you guys. Did anyone notice those professors when they walk by, they stop by and look in? Nosy. They want to see, I guess they want to see who's in there. What student might show up for their Math 7 course. Yeah, they're looking for you. I'm gonna lock that door next time, so they can't walk in. Now, here's where we're back in chapter 5. Guys got a handout here for you, of course. But let me do a little recap where we are. And I did this. Hang on just a second. Please remind me, did we get to a chance, an opportunity yesterday to do what I call conversion factors? To change from degrees to radians or the other way around? I think we did that. Okay, part 1, let's do this. I got some stuff to do here. The unit circle. Circle of radius 1 is the most convenient for what we're doing here in math. And we did something with that yesterday, but let me remind you, before I jump in, do some things here. Those conversion factors, if you need to use them, theta, from the Greek alphabet, if that angle is given to you in degrees, and for some reason you would like to convert to this new measure called radians, easily done, you're going to use a factor of, what was it guys, pi over 180? And that'll quickly convert this now into, right here, theta expressed in radians. If it's the other way around, say theta is in radians to begin with. He said, wait, Professor, I'm not very good at radians, I like to convert it back to middle school degrees. You're gonna multiply by a factor of, guys, I think it's what, 180 over pi? And that's what we were discussing, I think, right at the end of class yesterday. And that will convert this into, right like this, theta in degrees. These are my conversion factors. Because right now, if you've had no experience with this, and I walk up to you in the hallway and I see you, and I think, PK, I'm thinking of an angle of size 3 pi over 4. She said, Miss Ramsey, I'm glad you're thinking of it. And she moved on. I'm going to lunch, Miss Ramsey, why? No, PK, I want you to convert 3 pi over 4 to degrees. Take it back to middle school for me for some reason. I just walk up to you and say, what is 3 pi over 4 in degrees? How many students know? All right, see one hand going up, and the other. See another hand going up. So guys, if I think 3 pi over 4, and I will reflect back to middle school, and where the middle school teacher gave it in a different way, he said, well, if you gave it in radians, Professor, which I did, 3 pi over 4, and you want to use a conversion factor to find what it looks like in degrees, here we go. Pi's cancel. I think this goes into this 45 times, and 180. 3 times 45, what is that, 135? Help me out. So 3 pi over 4 is equivalent to 135 degrees. So if my mind messes me up and radians are difficult for me to work with, you can easily in your mind convert them back to middle school and see what we're talking about. So we discussed somewhat of that yesterday. Now though, part 2, here we go. I gotta get back to this unit circle. Oh, there's a ton of things to be done here. But I think you're gonna like it. An angle, I think we had an angle of some sort yesterday. I think what it looked like. And there's this. And we all agree, Professor, of course, that's an angle. And then I enclose that with a circle. Might look something like that for a reason. And then we talk about the circumference of the circle and the piece of the circle, the arc that's being cut out. And then a discussion about the radians and why radians exist. We did, I think. Yes. What I have not had a chance yet to do is we need to label, eventually, we need to label with coordinates those points on the angle and on the circle. That's the next task. You've got the circle there staring at you. They want you to label those points of intersection on that circle. I'm going to start out with, guys, my circle's not drawn to scale. Bear with me, please. Let me move it over just a little, maybe a little bit better if I do this. They look worse. That's it. It looks like this. I'll put it this way. But I need some space to work here. Okay, let's say it looks like that. I'll give you more space. If this is a unit circle, radius 1, mark that, this radius is 1, and all of a sudden you see Professor has this for me. He's placed inside there, that's why I wanted to get some space, a grid, X and Y axis, that might look something like this. When I line it up. And I know from Algebra 1, way back in middle school, I have what, 4 quadrants? So I use that grid, I divide the plane up into 4 quadrants. So there's quadrant 1 over here, quadrant 2 is here, quadrant 3 is here, and quadrant 4. Woo! me to know that. That's just from the sheet of graphing paper. You've got 4 quadrants, quadrant 1, quadrant 2, quadrant 3, quadrant 4. So when I was telling, if I see PK in the hallway and I ask her, PK, I'm thinking of an angle of size 3 pi over 4, she may in her head quickly say, Professor, think about 135 degrees. Then I would know, and she would know, it's over here in quadrant 2, if I should sketch it. Now why? Because when I start labeling here, we start labeling with 0 at this point. And I'm going to put the little degree marker right now. 0 degrees. If I move, and your textbook says move in a counterclockwise rotation, that means start here, this is the initial side always, and you move in this direction, which we were thinking you would. If I get to this point, move from here to there, I'm up here, and the angle is 90 degrees. Place that right here. That is representative, so put a point there. Representing 90 degrees. If I start here, move counterclockwise all the way around half the circle, I'm at 180 degrees. If I go back to the initial side and rotate counterclockwise and go down to here, this represents 270 degrees. And if I start here on the initial side and go all the way around, making a complete revolution and get back to where I started, I could name this also 360. One complete revolution on the circle. Is that true, guys? Now, here's the task. After I get the angles. They're asking us, now this can be a little tough for us sometimes. They're asking us not only that, but name the coordinates. I'm talking about coordinates of these points. I'll put it here like this, and with your help, let's get these out of the way first. Now these are the easier ones. Can anyone tell me if this is a unit circle? And we start at 0, what might be appropriate to label the x and y coordinates as at this point right here? 1, 0. 1, 0. It's on the x-axis. If I ask you what might be appropriate when I get up to here to label the coordinates of that point of intersection as, it might be appropriate as what? 0, 1. I'm hearing it. I reach 180, that point of intersection would have coordinates of, help me out? -1. 0, you're over there. 270, it's down here. Coordinates for that point there would be 0, -1. And of course, if I get back here after I do one complete revolution, I'm back to 1, 0. Is that true, guys? So let's go play a big part here shortly. Big part. You agree so far? Now, Philip, suppose I say, okay, that's fine. We see those. Now all of a sudden, Philip, I say this. Now I made my sketch a little larger. I say, Philip, let's think this angle as 30 degrees. This angle. That's a 30-degree angle. Now notice it has an intersection point right there with my circle. I need to name its coordinates. Like we easily identified these coordinates in blue here on the others. This one's a little bit tougher. But I need coordinates for this point right here, Phil, and this is for a 30-degree angle. Any idea? I'm not putting you on the spot, just trying to get a discussion started. See, if you're thinking like this, Professor, I've got to be clever. 90 subtract 30, maybe will give me a 60, this 20 something, 60, something else. And wait, I realize what you said. I don't think it's going to take me where I want to go. Do you?
We can make it in radius.
Oh, you can change. Oh, look at this, look at this. 30 degrees. Here we go. Now, if that would help, look at this. 30 degrees. By conversion factor, it's in degrees right now. So I will go into radians for some reason, multiply by that factor, pi over 180. Do a little canceling here. Is 30 degrees equivalent to, in radians, pi over 6?
Yes.
Here we go. So I could write this, oh, okay, so 30 degrees is equivalent to 5 or 6. That's what I want here also, but I'm looking for the coordinates of the point of intersection. Like you guys down here quickly said, Professor, it's 1, 0 there. Up here, Professor, 0, 1. And this one over here on the left was negative 1, 0, x and y coordinates. If you're down here, it's 0, negative 1. Just like on a sheet of graphing paper. But Professor, now you're asking me for 30 degrees. What is it? Is it 1, 0? No. Is it 4, 1? No. I'll tell you that much. We gotta find out what it is. See, hang one up, yes.
Did that have something to do with like, I wanna say SOHCAHTOA, but something with the
Oh, don't go to
triangle?
SOHCAHTOA. I know you guys are from high school and so forth and so on. They use that, what, SOHCAHTOA sort of remind you of what sine was and cosine. You guys heard of that? Yes, I had never heard that before. Nah, I don't like that word. One of my students used that word in class and I had not heard it. I thought they were mad at me and would call me a name. I thought, you call me a name? SOHCAHTOA? I never heard of it. I didn't know what it meant. No, we're gonna stay away from SOHCAHTOA. Something else. I gotta be, and this is hard. Got one here. Yeah, Karina.
Maybe triangle and true
Oh,
triangle.
hang on. Are you telling me if I'm desperate? No, we are. We're trying to find the coordinates of this point here. Darn it, Professor, why don't you stick with this one down here, 1, 0. And stick with this one, 0, 1, 90 degrees. Stick with 180, negative 1, 0. 270, 0, negative 1. Stick with those, Professor. It's right there on the edge where I know for sure what the coordinates are. If I go inside, Professor, pick up now 30. I need the coordinates of that. Now she says I might be able to find that. I'm going to use the red marker here. If I drop a perpendicular down to the x-axis, I've captured that 30-degree angle in the corner. This is a right angle. And I think every student would tell me if I constructed a right triangle, that angle in the top there is an angle of what size? 60. Put that in red. This is a 30-60 right triangle. Now I'm trying to find those coordinates up there, x and y. In other words, I'm trying to find this. Let me erase this one. I'm trying to find x, I'm trying to find y. And then I'll put them here. Does anyone have an idea? I don't know how much geometry you remember when you were back in geometry. It's a 30-60 right triangle. Does anyone remember anything special about a 30-60 right triangle? And most students will have forgotten. Guaranteed. I think all my students probably have had a geometry course one time or the other. There's something special about a 30-60 right triangle. Let me ask you this before I get back to 30-60. Does anyone remember anything about a 45-45 right triangle?
Yeah, same sides.
It's an isosceles triangle. Two sides are the same length, right? Two sides are the same length. That's easier to remember.
The side in front of 30-degree angle is twice bigger than the side. No.
For a 30-60?
Yes.
Okay, here's what I'm going to do here. I think you had there. The side opposite to 30, hang on a second here. Get this out of the way here. Look at it. Now keep in mind, I have 30 right there, and you know I meant 30 in the corner here, of course. Trying to get some space. We have the radius to be a 1. That radius is acting as, here comes the word, it's acting as the hypotenuse of that right triangle. It's the side opposite the right angle. And it has a length of 1. Well, here it is. I'm looking for these two lengths in red. This x, the base of that triangle, and the dimension for the y of the vertical side. Now he's telling me, Professor, I sort of remember something about, especially about a 30-60 right triangle. The way I remember it, the side opposite to 30, which in my case over here, should be 1/2 the length of the hypotenuse. Always. I don't care how large the triangle is, how small it is, if it's a 30-60 right triangle, the side opposite to 30 is always 1/2 the length of the hypotenuse. Well, my hypotenuse is 1 in length. Therefore, the side y I'm looking for immediately is what? What's What's the length there? 1/2. It's 1/2 of 1. From that relationship for a 30-60 right triangle. Now, can someone come up with a nice way to find the base, the x, I need to find it also, and when I find it, I'll put those two up here. Then I'll have the coordinates. Does anyone have an idea how to find the base down here, the x? And there's another property for right triangles that maybe you want to apply here to find it, or some students may have in their mind what it should be right now. Does anyone have an idea? Oh, we have forgotten geometry. What was that?
People with the.
Yeah, Pythagorean theorem, wasn't it? C squared is equal to a squared plus b squared. Hypotenuse squared is equal to the other two sides squared and add up. C squared is equal to a squared plus b squared. I'm going to apply Pythagorean theorem on this right triangle with the numbers you see right now and hope to get where I want to go. I got 1 here. That means this is 1 squared. Down here, they have in the formula, Pythagorean theorem, as a, I'm going to call it x. That's unknown. This side over here, y in my case, we found to be 1/2. Of course, being squared. That's Pythagorean theorem. Now I should be able to find what x is, I hope. So guys, this becomes, I'm patient, 1 is equal to x squared plus what, 1/4? Move that 1/4 over, subtract it 3/4. I don't want to do it too quickly. Do a square root, you end up with radical 3 over 2. That goes here. Put in black. This now is radical 3 over 2 with the help of Pythagorean theorem. Now, quick check before I put my coordinates in. Quick check. If I square this, a little check. If I square radical 3 over 2, that's 3 over 4. If I square this one 1/2, I get 1 over 4. If you add them up, 3 over 4 after you square plus 1 over 4 gives you what? 4 over 4, which is 1. And that's what I want here for that unit circle. Now, what are the coordinates? Radical 3 over 2 and 1/2. Now, let me give you an idea where I'm going. If you see all this, you may say, Professor, whoa. Whoa, Professor. It's been heavy. So, I have to do this, Professor, each time for every angle on that circle. For example, I just did for 30. That's my angle. If I redraw this and put it inside here in the corner here this time, let's look at maybe a 60. Numbers change. Supposed to put a 45 in there, Professor, not 30. The coordinates change. And Micah's really terrifying would be if I put 12 degrees. Now you gotta find the coordinates. Now I'm gonna do one more for you. But hang on before I do one more for you. With that circle, please tell me, if I've got the coordinates for 30 degrees, and by the way, this will be used in grad school, PhD programs, no matter where you go. 30 degrees as for coordinates, radical 3 over 2 and 1/2. That's not going to change. No matter where you take your math, like you leave us. Now, with your help, my help here, let's do this. Can anyone be clever enough to tell me, suppose I reflect that point across the y-axis. My black marker did not work. I actually need it to work. I'm going to reflect it across the y-axis and ask you guys a question here. Okay. Does anyone think they might be clever enough? I'm in quadrant 2 now. Tell me, what would these now look like if I went over to quadrant 2?
X is 1 of the minus.
Hang on. It would be how much now?
X is 1 of the.
X will be negative. Negative radical 3 over 2 And does the y stay the same? And why is that? Because if you're in quadrant 2, way back in algebra, guys, if you plot any point on a sheet of graphing paper, and it fell here in quadrant 2, you're guaranteed the x is negative and the y is positive. Guaranteed. That's why now this point looks like this. Now, let me reflect it again. I'll ask you an additional question here. Now, suppose you take that original point and you take it through the origin. Look at this. And it lands in quadrant 3. At first, from algebra 1, if you're down in quadrant 3, your point falls in quadrant 3, you have negative, negative. The coordinates are both negative if you're down in quadrant 3 on a sheet of graphing paper. Now, can anyone tell me if I do that, I'm running quadrant 3, what would this point look like then, here, reflected through the origin? Someone name it for me.
Negative root 3 over 2 and negative 1/2.
That's exactly what I want to hear. Same numbers, but both negative. I have one more reflection. Let's take that original point, I'm doing all this for a reason. Let's take it down to, through the x-axis, do it like this, guys. Through the x-axis and land in quadrant 4, now it's here. And if I'm in quadrant 4, I know and you know. On a sheet of graphing paper, the coordinates for signs are those. So what would that point look like, this point, reflected across the x-axis and land in quadrant 4? Radical 3 over 2 and minus 1/2. Whoa! Lord! Look at that. Somebody walk in and see what we're doing in the this class and profession, you included, all crazy. What are you doing? Look how crazy that looks. Looks cute. Look how crazy it looks. That's making sense. Now, I've got 4 points here to work with. Now, we'll throw it out. Now, I'd like to know, watch carefully. I have to slow down a little bit here. I'd like to now know, yes, this is the point in quadrant 2. You guys help me out with the coordinates. Now, I'd like to label the angle that has those coordinates. In other words, this. Now, I know I'm marking my sketch up. Here goes. That's the angle. And you always measure from over here, the initial, over to there. That's the angle whose coordinates are those. I'm going to throw it out there. Does anyone have an idea of what size angle is that has those coordinates based on what you see up here? Bill, go for it.
150 degrees.
He says 100, professor, that's 150 degrees if you start here, counterclockwise, like the arrow shows, and you stop there, and its coordinates are up there. He says, professor, that's a 150 degree angle. You think it is? Because I think originally this was 30, wasn't it? Wasn't it 30? And would you not expect this to be 30 over here also? If I just take it directly across? Is that true? So 180 subtract 30, because this is 180 here, isn't it? So 180 subtract 30, is that the 150 he wants me to do here? Yes, that is 150. I'm going to put it in radians here for you. So this is 150. Oh, thank you so much. I'm 150 degrees. Let's convert it. Guys, is anyone to think they know what 150 looks like? I use a conversion factor. What does it look like in radians? Go for it.
5 pi over 6.
Thank you. Now you use a conversion factor to do that. Philip, you may have to help the class here. That one's out of the way. One of my sketches is getting all marked up here. Now you guys give me this one. Down in quadrant 3, the coordinates. I'd like to know now, going all the way back, please bear with me. The angle there is from here all the way around and stops here. Who has an idea of what size angle am I dealing with now, down in quadrant 3, that will have these coordinates? And Philip says he knows. What you know? Philip, what is it?
40.
I think you're off a little bit. By the way, did we say this is 30 right here, guys? just thinking about it on the other side. Would you think maybe this is 30 also? The little angle in the corner here? Is that 30, you think? If you think about what's going on here, and is that 180 plus 30? What is 180 plus 30? Is that 210? So I'm looking at a 210 degree angle down here. We'll place it right here in blue. Does anyone think that what 210 looks like in radian measure? What is that?
7 pi over 6.
Thank you. It's taking a little time here. I'm finally ready to move into quadrant 4, I think. Quadrant 4 you guys gave me earlier. These are the coordinates, Professor. But what angle is it? That means you are now, look at that sketch. Oh my goodness. June, I don't know how you can put this together for me. I hope you can make it look better than mine. We'll start here, go all the way around, guys, to here. Now, I'm really messing this up. It needs to be done. Does anyone think they have an idea what size angle is that? And that is what is associated with this. Who has an idea? You start out there. What size angle is it? I'll tell you this much, it's bigger than 270. And it's less than 360. What is it?
300.
Tell me again.
330.
300 or 330?
330.
330. I'm hearing 330. Hang on, guys. Would we accept, look at this, I love this. I start out with a 30 here. I think, you know, if I reflect that, that's 30 right there also, isn't it? Right beneath here, is that another 30 degree angle if I was to look at it like this? And then the entire circle is what, 360? So 360 subtract what? That 30, does that leave 330? Is that 330 degrees? Right? I agree. Thank you. And that, its point is right there. So that's 330. We're gonna put in radians, guys. Okay, I need 330 in radians. Go for it.
11 pi over 6.
Love it. Oh, my goodness. Now see some looks. You're saying, Professor, are you going to do this sketch again shortly and do it now for a different angle? You started out with 30 on this one and drove me crazy. Now you're going to do it for 45, Professor? Are you going to do it for 60? Are you going to do it for 10 degrees, Professor? We'll be here all the rest of this winter and spring and fall. If I went through and did every angle possible here. I did 30 for you guys. We're going to accept this. I'll organize it for you. Let me ask you this. We've got a short amount of time. Would it help if it has been done for you? Oh, look at this. It's been done for you. There's the unit circle filled in for you. We're not going to fill in all this with me and you and working together. We'll be here forever. It's already been filled in for you, and you said, sure, I have to look at it. I don't want you to memorize. It just makes it sense of like I did with that 30. And you'll see which one's special angle. Now, does this contain 10 degrees when you get it? No. Does 10 degrees exist? Yes. But it's not one of the special angles for math. We usually stick with 30, 45, 60, 90, 180, 270, those types. But those other angles do exist. But on this, just the special angles. Would it help if you had this? Rather than you going through this business. You get just a little dizzy here looking at all these marks. Right? But I did it for 30. So I'm not going to do it for 45. Nor 60. I could. Same routine though. We'll have different numbers that work with. Are we okay, guys? Woo. Now, I'm going to stick with this for a while here. Now, on the side here, I'd like to, before I do additional angles, do this. I need now to list the definitions of the 6, they call it trigonometric, spelled this way, functions. definition of the 6 trigonometric, reading my writing there, functions. And here we go back to functions. Now I guess the first day I met you, I'm sure I mentioned quadratic functions. The very first day. And we're still talking about functions. Except now they're trig functions. And we've got 6 of them. I will list them for you, show you what they are, and these are the shortest, most basic definition you'll ever see in your life. Because if you're asking for a definition, and you go online and look for a definition of something, it's usually carrying out lots of words to define something. Not these. And we'll start out. And by the way, there's 6 of these, and they're given names. First one is spelled this way, sine, the sine function. It's abbreviated S-I-N. I'm moving theta next to it, sine theta. But we'll be doing this with an angle. So sine, S-I-N-E, that's the name of the function, abbreviated S-I-N theta. Now, what its definition, you say, oh, professor, if I go online, they're going to give me a big, long list of words. No. Here's the definition. I had better use a different color here. Definition is why? Now you try to find a definition looking like that. That's its definition. Number 2, 6 of these. Next trig function is given this name, cosine, abbreviated, C-O-S theta. There's this abbreviation, C-O-S, cosine, that's just the name of the function. Professor, what is it? What's its definition? X. Are you kidding? Number 3, tangent. Spelled this way, abbreviated T-A-N, theta. Definition? Oh no. Y over X. You can't go wrong with this. Number 4. Throw in secant next. Spelled that way, almost like secant line, secant here for a function. Abbreviated S-E-C theta. Definition? 1 over X. Number 5. Cosecant. Spelled this way. Abbreviated C-S-C theta. That's its abbreviation. Definition? 1 over Y. One more remaining, number 6. Cotangent. Spelled this way. Abbreviated C-O-T of theta. Definition? X over Y. Whoa! You say, Professor, I like those definitions. The blue? Oh, those are the briefest definitions I've ever seen in my life. Those are brief. I haven't used them yet, but those are the definitions. Now, some of my students who may not have had experience with trig, you may say, there's some strange words, Professor. Sine, cosine, tangent, secant, cosecant, cotangent, but look at their definition. Now, I should add, though, as I'm doing this, make a connection. Those definitions in the blue have a connection to this. Were we discussing the X and the Y coordinates on this over here? That's what we're discussing here. That's where those X and Y's will play a part. It's back to that unit circle. So I better point out that these are the 6 trig functions based on the unit circle. So I can go back to the unit circle and apply those definitions. Wow. Now, one of these days, you guys will be in grad school. In fact, I have a student who just contacted me yesterday, was it yesterday? The day before. And he's gonna be in town pretty soon. I'm hoping he'll get here before your class is over. But this guy needs to come in and tell you what he's doing now. He's doing something in research I had no clue. He's described it to me. It's ran to the lost. But he's doing something down in research. He needs to come in and talk to us. Now, grad school, same. Not gonna change. Now what am I gonna do? On the side here, before we take a break. Here we go. I'm gonna apply those blue definitions to some of this. Now, I started out with 30 degrees. I know my graph is all messed up here. We'll start with 30. We'll just call it pi over 6. I like to find sine of pi over 6. Let's apply that. See what it is. Sine of pi over 6. Well, the definition says why. Well, did we, since it's all messed up here, I think it's up here. What's the y coordinate? Is it 1/2? That's the sine of 30. That's the sine of pi over 6. They just want the y coordinate. And I think the y coordinate was up here, wasn't it, for 30? Let's try cosine. Cosine of pi over 6. Here we go, guys, which we had right here. That's a 30-degree angle. We had it up here, and I found it. Cosine's definition says, write the x. Well, the x is radical 3 over 2. There's the cosine. Tangent of pi over 6. No problem. If I use my definition, be careful right here. It says now place the y over the x. Well, look back there. The y was 1/2 over the x, which is what? Radical 3 over 2. And you need to clean that up. That's y over x. 2's canceled. Rationalize. And guys, if I rationalize this with the 2's canceling, what is that? I think it's radical 3 over what? 3? See if I'm right. If you rationalize, it's a radical 3 over 3. Next, I got tan secant, S-E-C, theta, in this case pi over 6. Definition says if you want to find it, here's the definition. Place 1 over x, looking back there, the x was 1/2 coordinate, so it's 1 over 1/2. Oh, that's nice, that's 2. There's secant. Go for it, yes.
I thought x was radical 3 over 2.
Which one was it? Oh, right here.
Yeah.
I'm looking at the next one. Radical 3 over 2. Thank you for catching that. 1 over radical 3 over 2. Where am I? Right here. Now, can someone clean that up real quick for me? 1 over radical 3 over 2, cleaned up, rationalized. Can someone tell me what does it look like? On the side there.
1 divided by 10.
Something better than that. What does it look like? No radical in the denominator. Cleaned up. 2 radical 3 over 3. We have to clean that up. Next one, I think it was cosecant. I think this is one I had in mind when I was writing this so quickly here. Cosecant of pi over 6. Well, if you want to find it, it says place 1 over y. Yeah, the y back here was 1/2. That's one I was thinking about. So it's 1 over 1/2. 2. There's only one left. What was it? Cotangent of pi over 6. Hey guys, pi over 6, cotangent says please place the x over the y. I think the x was radical 3 over 2. And place that over, let me squeeze it in here. Over what, 1/2? And this was easily done. 2's will cancel. Looks like it's radical 3. Wow. Do we have all 6 done? Now we're going to take a break. Here, sure. Joseph. Mathematician. Joseph, suppose now, after the break, I I ask you now to find all 6 of these again. Not for pi over 6, I did pi over 6 for you. How about 45 degrees? So now I ask you to find all 6 again, but do it with a different angle, not 30, but 45. Would you expect the numbers to change? They will change, that's the problem. Then I'm gonna ask you to do it for 60. Will the numbers change on the unit circle for 60? Yes. And goodness gracious, I would not ask you, but it could happen, 10 degrees. Find sine, cosine, tangent, all 6 for 10 degrees, that would be a nightmare. You just find the coordinates, like I did here, for my 30. Answer that. Or use a calculator. And the calculator will flash out on the screen for you real quickly. You may not know what it means, but it's on the screen. And you write down the answer, and you smile, and whoever teaches that course smiles, and you got it right. And then someone says, what does that mean? I don't know, I just saw it on the screen. I just saw it on the screen, it flashed at me. I put it down, and the teacher gave me credit for it. We all smiled, and I got an A. What does it mean? Oh, I don't know what it means. Okay, so I'm trying to make some sense of this, what it means here. Guys, how's that look so far? Okay? Now, can Ramsey do all this for us, or Joseph do all this for us? No, but when you get back to the break, I am going to do just one more for you. I will go through this crazy business and see what 45 looks like. Sine of 45, cosine 45, tangent 45. But I'll have to find the coordinates. I think it's going to be easier with the coordinates for 45. Before we close down, does anyone think they know what the coordinates, my coordinates for these? Does anyone think they know if I go through the same routine? I'll have a triangle drawn inside here for you after the break. And I go through the same routine, except this time it's 45 in the corner, which means 45 up here. 45, 45, right triangle. Does anyone think they know what the coordinates now would be? Go for it.
Square root of the like 2.
Radical 2 over 2. For the x and the y?
Yes.
For both. That's going to be an easy one for you guys to remember. Mine was radical 3 over 2, comma 1/2. After the break for 45, it changes. It's radical 2 over 2, radical 2 over 2. They're the same. And we got to see why. And then go through and find these for 45. And then the others I'll just go ahead and give you. Okay? Guys, this will help. Now, before we take a break, I'm going to get all this to you. Are you going to be allowed to use this on the test? No. No. Now, you can take it out and show your friends how cute it looks. And you may memorize this thing in a different way than I do. Students come up with different ways. I had a TA a couple of semesters ago. She had a better way she showed the students how to memorize these numbers. Okay? Rather than just trying to remember, she had a little trick of some sort. Pick up with the numbers. But I'll get this to you later, guys. Now, I've got a quiz later on today. I'm going to give you 30 minutes for this quiz. I need my time here. So we're going to stop around, probably around, what, 2:50? I guess, around 2:50.